Hi, thank you for joining me in this live stream session. My name is Venkatesh Raghavan. I'm the product manager for query processing in Greenplum Pivotal. So today we're going to talk about an interesting topic about optimizing complex queries, which are usually found in BI tool generated queries, as well as any workloads that come with mixed workloads where it's analytical queries and transactional queries. We are going to zoom in. It's a large topic, so we're going to zoom in on a small subset of these complex queries. And one is the aggregate queries and nested subqueries. So the mission of any query processing team or a project is to make sure your queries meet your SLAs. So we want to make sure that any customer that you are servicing your queries is as fast as possible with less memory footprint as possible. So that's usually the goal of any query processor. Transactional systems, there are a lot of transactional systems. We have 30 plus years of people developing really good transactional systems. And most of those queries and most of these workloads have a lot of joins. And they do an awesome job of doing join ordering. It's really great, and they're pretty good at it. So join ordering is their main bread and butter whenever they come. It's like 10-way joins, 20-way joins, 100-way joins, and they do an amazing job. It's a very principles approach. There's dynamic programming, greedy algorithms, many list of work that has been done there. So it's really good work that has gone into, and because we are a Postgres-based system, we get all of those good stuff of join ordering into our product. But there's something beyond join ordering, right? So let's take a simple example of TPCH query 6. And it has a TPCH query. This query has like 6 tables. It's very straightforward with aggregates. So if you see all of the possible plans that you could generate for this query, there are billions of plan alternatives. And among them, what are the ones which are join ordering? Meaning how many different combinations of join orders you can have is like 100,000, less than 100,000. But the rest is a large amount of space of everything else. That means something else that you need to process. And that's what we want to focus on to this talk. It doesn't undermine the effort for the join ordering, but this is like, hey, let's talk about the rest of the landscape that we have. So what is this everything else? The everything else is it has subqueries. You have subqueries in the project list. You have subqueries in the having clause. You have subqueries in the where clause of the select statement. You have aggregate queries like min, max, average, and different things. You have grouping sets, window functions, common table expressions like with clause. You want to modularize your SQL and you create with clauses. And you have ordered data like ordered aggregations and sort by. Static and dynamic partition elimination. And for us in Greenplum, because we are a parallel system where it's a shared nothing architecture, except for replicated tables, but generally it's a shared nothing architecture where data is resident on multiple segments, so distribution. All of this is that everything else, like which goes beyond for any complex query, right? So what we want to focus in GPDB is that, yeah, we're getting all of this awesome 30 years research from Postgres and join ordering, great. But there are some things with the data warehouse with all of these everything else, like aggregates and nested queries. If we get it wrong, we are in a bad place. So that's what we want to focus on. So it could be a hit or a miss if you just let status quo be as it is, okay? So the outline for today, what I want to share with you is just focusing on this everything else. And among the everything else, I'm just going to take 2 topics. And one of them is correlated queries, and one of them is aggregate queries. And they themselves are quite vast. We can't possibly cover all of them. So I'm going to present 2 things in each. So 2 of them in correlated queries, and 2 of them in aggregate queries. And what is currently there in the system, and what is upcoming, and what exciting new things are there for GPDB 6 when we release it. So every slide has these markers, T1, T2, 3T, 3.4, which tells you which topic I'm trying to cover. So let's start off with subqueries before we go into correlated subqueries. The subquery is a query that is nested in another query. So a query, for example, here, this subquery is nested inside the where class. The blue represents the outer, and the red represents the inner. So the blue, so here, if you have, there is no correlation or no variable from the outer that is coming into the inner. So this is a simple subquery. But then you can have correlated subqueries where you have this inner part, which is the red, which is now referring to something which is in the outer. So that's a correlated subquery. So this is the correlated subquery is what we're going to talk as the first topic of our talk today. So impact of subqueries. Any BI system or any analytical system you want to do, GPTeX, MATLAB, anything, you're going to write complex queries with a lot of correlations. Just as a sample, if you see TPCH and TPCDS is our benchmark queries, and 40 to 20% of these queries are already having correlated subqueries. So imagine if you have complex analysis when you do automated cars or something like that, or location-based services for food, you're always going to match something with something. Some location, some ID, some transaction of a stock, you're going to have these nested subqueries. So if you get an inefficient plan on petabyte of data, which is distributed across different segments, you may land up in a pickle where the query never returns, right? That's one of the reasons why people want to have a big data solution like Greenplum. So what can we do when you have a petabyte data and you have these complex queries? How do we solve that? We solve that, and this is not everyone who works in this space have thought about this, and some of the ideas are, let's try to remove let us remove those nestings when you have correlation between outer and inner side. Let us try to decorrelate them, and let's make them into joins. And you will say, hey, why suddenly joins is suddenly going to make everything well? So joins per se may not make everything well, but if you have a localized, parallelized join, suddenly you are making this big monolithic query into bite-sized things that can be executed into each node. So why we want to decorrelate them and make it into joins is to make sure that we can take the benefit of parallelizing joins and localizing join operation. So there is a talk by me about how to pick distributed data distribution so that your joins are benefited. There's a link here, and we can post it later on the stream for you to refer. So in old tales, they always give the conclusion away first before telling everything. So this is the conclusion of this section. What do we do? What does GPDB do for correlated queries right now? So correlated queries can happen in many different ways. It can happen in a where class, that is the filter. It can happen in the project class, where it's a select. It could have multi-level correlation, where one is like a babushka doll. It's like one is correlated with another, which is correlated with another in the outside. So you could have a multi-level correlated subqueries. You can have correlated subqueries with group by and inequalities. You can have correlated subqueries which you have to make sure that you return one row or you error out. Or you can have correlated queries which are then in the select class which has multi-levels of correlation. So in GPDB as we stand right now, for all of the case except the bottom one, which is the correlated subqueries in the select class, we always generate a join which can then be parallelized. So this is awesome. So that way we can generate efficient plans that can come in which will meet your SLA. So let's take the first. So among these tables, I'm just going to take the first two. That is, if you have correlated subqueries in the where class with ORs, and correlated subqueries in the project list, which is the select class. So let's look at a simple example. This is based out of parts. Parts is a table in the TPCH, and you can think about parts table. So basically what I'm trying to say is, hey, I want a part which has a size greater than 40. It could be price greater than 40, or it could be color blue. And then that part type, I want to see if that part type, what is the average cost, average price of that part type, and make sure that I am greater than that. So you have list of all parts. I want to make sure that the part size is greater than 40, and its average retail price is greater than the average of that part of that particular type. Okay, so how does the query plan look like? So you have this blue part, which is the outer. You read all of the parts, and then you check, hey, this sigma is the select, and you say, hey, is the part size greater than 40? If the part size is greater than 40, I then say, hey, what is your part type? And then I'm going to find out, based on your part type, I'm going to find out the average price. And once I get the average price, I check my condition. So I have this OR between these two predicates. That means for each part here, I need to find out the part type and find out the average price of that, and then check with it. As you can see, that means if there are two parts with the same type, I recalculate this twice. And that is inefficient. If you have a petabyte of data in that tuple, in that table, this is going to be a very inefficient plan. So how do we do in GPTB? What we do is we say, forget about what the particular part type is. For each part type, I'm going to generate average price of each part type, because I'm assuming number of part types are going to be much less, right? So I can generate the average price of each. Then I do a left join based on that part type. So I know what is the average price of each part for each of that row. So this whole group by doesn't get repeatedly executed. It just executes once. And this join, now I can make sure it's parallelized and it have local joins. Awesome. And then I just do my select, and now this whole average bias just becomes a tuple, or one of the columns in that tuple that I'm going to be having the join result. So as you can see, by making it into a join and parallelizing join, you hit it out of the park. All right? So let me give you a teaser example. Okay? So I have this part table from TPCH, which has about 2,000 parts. Very small table. And the same query which we talked about, without the optimization, it's 290 milliseconds. With, it's like 42 milliseconds. That's a good optimization of around 7x. So imagine this is just for 200 parts, 2,000 parts. Imagine you had 1,000,000 parts. What would be a benefit?
That is 290 milliseconds, and this is 42.5 seconds.
Yep, milliseconds. Sorry, it's a millisecond. My mistake. It's millisecond. Sorry about that. Thank you for catching that. So the second type of correlated subquery is you have in the project list, you have the same form of correlation, and you have an attribute level correlation between the outer side and the inner side, which is the PG attribute. The same way, so here you scan the PG attribute, and then you do an aggregation on top of that, where you check whether the same OID is there. Okay? So just like this previous example, we do a left outer join by grouping on whatever that you are trying to compare, and then do a left outer join based on the join condition. It's the same principle for whether it applies in the select class or whether it's applied in the project class. So without optimization, it's about 6,500 milliseconds, and with optimization, it's like 95 milliseconds. So you will have, this is for a TPCDS benchmark. I just took the benchmark, I put the schema, and it's a catalog table. I just ran it on the catalog table. About 70x performance improvement. So those are the two topics in regards to having correlated subqueries in project list. So now let's go on to the next topic of group by over set operations. So aggregates come in different flavors. You can have inbuilt aggregates like minimum, maximum, sum, max, sum, average, or you can have user-defined aggregates. So those are the two kinds. So let's look at a simple example from TPCDS, which talks about, hey, you have web sales, you have different forms in which sellers can sell their product. So let's try to find out what are the unique number of customers that I have across all of these opportunities for selling. So here I want to have catalog sales as well as web cells. I want to union them and then figure out what are the unique set of customers that I have. That is the query that you have. So you have a union. Any set operation, it could be an except, it could be a difference, it could be any of those. Intersect, sorry. And then you're grouping by to find out the unique customers so that you can go and send out promotions for these unique customers. So a naive way to do that is to say, hey, just do a union all between all of the customers from web, all of the customers from catalogs, and then do a group by aggregation on top, and everything will be happy and dandy. But that's not always the good thing, because you could have many people who buy many things within each web sale, and many people who buy things from both. So you can have a lot of unnecessary work when you just want to have unique number of customers that are coming out. So the better way to do it is you push this grouping aggregation all the way down and say, within each of those avenues, I'm going to prune away all of the duplicates, then union it, and there could still be some duplicates across these two sales opportunities, and then I do a group by again. This is all the examples I'm using today are very simplistic, naive examples to, to hit home a point, saying that you could have, for example, different views. Many customers have this, different views that you have on different sets of data, and then you aggregate them together through a union, right? What are the different, there are different avenues of you selling, a restaurant can sell food, right? Grubhub and DoorDash, other things. So each one you want to mine them to figure out unique customers, all different ways, walk-ins, and then you want to group them, aggregate them to then send out promotions. So these are, you can have simplistic views or you can have complex views on different, like say for example, different geographic stock exchange where you have different stock exchange and you want to do different transaction, and then you want to have a global aggregation of these stock trades. So this union or a set operation between different views is a very common thing. And you will always have some form of a group by on top that you want to aggregate or summarize. This is all about summarization, like analytical queries. So let's take a simple example, foobar, and you have about more than 1 million tuples in the first one, where there are 1,000 unique columns in that. And another bar which has like 100 unique columns. It's a smaller table, right? So the same way, I'm going to do a union all and then a group by. What we found is just for this small table, which is not doing much, it's just doing a scan and then finding out unique values. It's 2x better, approximately. So imagine you have a complex query. You could push the group by down. Then you could push correlation down. Then you will have, imagine how much benefit that you will get if you have a simple operation of pushing group by below set. So the next topic is aggregate queries over joins. So aggregate queries, as I said, is like sum, max stuff, which we already talked about. But many times you join two things, and then you do an aggregation. So for example, you have revenue, you want to find out each store sells a product, and the store gets certain things in return, as returns back to it. So now what you want to say is, I want to know which store is trying to having a lot of returns and find out why that this store is having a lot of returns. So what you have is and the orders are split into line items. So you have a line item table, you have an orders table, and then you have returns which are marked into the line item. So you want to find, and then the order has the store number, right? So now what you're saying is, I'm going to try to find out which are the ones which are returned, find out from the order which is the store where all of these returns are coming, and then aggregate based out of store, how much loss did I have? And then say, can we go and address, have a customer satisfaction survey or something, or why, or ask a question, was this product okay? Did someone help you? All of these analytical queries can happen only when you can find out which is the store that you want, all these returns happening. So in this query, what you have is you have a join key. So each order has an order key and each line item has an order key. So you're going to join them. And you are under this assumption that on every order, all the line items in this order are each is associated with a single order, and that order is associated with a particular store. Like, that's a very simple, it's a realistic assumption. So the second one is you are going to group by the store. So you're going to group all of these, I want to group by the store to find out the loss that I'm making. And then I have this aggregation operation, which says I want to sum up all of the loss. And the loss is basically what is the price, what is the discount I got, and that is the loss that I'm making. So I want to sum up all of that loss based for each store. So how could you do it in a naive way or a straightforward way? Each item, you will scan through them and find out which are the items that got returned. And then you say, for those items, I'm going to compute what is the loss that I made. And then I'm going to say, hey, then join them with the order to find out which stores got these returns. And then I'm going to say, I'm going to sum up the losses. And that is my loss based out of that store. That's a very simple query. But as you know, I love coupons. I don't know whether you know, but I love coupons, and I'm sure you love coupons. When you go and you get a stack of coupons and promotions, you go to a store and you buy a lot of stuff which you may not need. And then you come back and return them. So you'll end up having line items because you bought more than what you wanted to buy, and then which was an awesome deal going on. And then when you got home and your spouse or someone else told, or yourself, got guilt saying that, hey, I have to return all of them or some of them, and you return them. So you will end up having for each order, you'll have many line items. All right? So you're going to scan all of them and then compute all of the returns. All right? And then group and then join them, and then you will compute the loss. That means if you return to 20% of every order, everything that you bought, that means for each one you will join with the order, and the 20% will become the join result, and then you group on top of that. That means the join got 20% more stuff than what you needed to do. So how do you optimize this? So what I can do is, for each order, for that particular line item, L order key, I will group it. So I will feed less things to the join, and thereby reducing the amount of time that the join spends. And then what's awesome in Greenplum is that you can then divide this group by into local aggregation and global aggregation, right? So each order, for each segment, you're going to do a local aggregation of what are the orders, and then if you have distributed it on the order key, then you don't even have to need a local aggregation. That means each segment will generate the order loss, right? And then you join it with the order key. That means you have just reduced, everything is happening locally on a segment. You don't have to shuffle anything. And then you join it on the order key, and then suddenly you already have the sum of individual order losses, and then you join aggregate them into by the store. So it's a very simplistic idea, and it gives a lot of money for the effort. So a teaser, again the same foo bar. I have more than 1 million tuples there. I have a group bin column which has 10,000 columns. I have a join column which has 1,000 columns. Then I have another bar which has fewer. All right? Then I have this query where I have some join condition, then I have a select condition, and I have a grouping condition on columns from both sides. In the previous example, the grouping was only on one side, but here the grouping is on both sides. Okay, just to make it a little bit more interesting. So without optimization, it's about 64 seconds, and with optimization, it's 7.4 seconds. All right, that's about 9x improvement. And this is for a small table which is not doing something fancy. All right, if you do min or count, it's even faster. Right, because here it's at least it's doing sum because it has to maintain state. If you do min, it's even faster. So this is a 9x improvement for a simplistic optimization that you can have on this. So eagerag is coming up in GPDB6. So the previous, all of the optimizations I talked about are already there in our existing product. You can enjoy that. But eagerag is coming up in our upcoming release of GPDB6. And if you download our code from the master, and you can enable a knob to have this facility. So what are the things that we handle in eagerag right now? We handled built-in aggregates. That means if you have user-defined aggregates, we have not yet tackled that problem. So sum, max, min, average count, we handle. The next one is we do not handle if you have complex expressions inside the aggregate from both sides, right? You one column from the join this side, one column from the join that side, and you add it and then do aggregation. We don't handle. We are in the process of investigating and figuring out how to cleanly do distinct qualified aggregates, where you have count distinct, min distinct, max distinct. And we don't do correlated aggregates. Sometimes, just like a correlated subclass, you can have correlation within the input to an aggregate. So you can say sum of P2 dot price multiplied by P1 dot price. That's where P1 is coming from the outer side. So we don't handle correlated aggregate function. It's rare. The reason why we don't handle it is rare that you write that query. Maybe we should rethink how we write that query. But you never know. Your BI tools may write such queries. And the aggregate functions are only on one side. So this is our first feature. So first time we are delivering this. So we are saying all the aggregates should be on one side so that we can easily do it. The next step, what we are going to do is aggregate is on both sides, and then how to do distinct qualified aggregates. So how do you take advantage of this? So we currently have a knob that says in optimizer enable eagerag. Currently it's set to false. That means by default you won't have the benefit. And if you want to use it and try it and give feedback to us, you should turn it on and try to see how it's benefiting it. Now the question that you may ask is, why is it on by default? It's coming. It's going to be on by default. But what we are trying, there are small kinks that are there with regards to, because if you are order, say for example, if everyone went to the store, and there are some stores which only take one coupon, and you bought one coupon worth of product and kept going back and back again. When I was a grad student, I did that. So I just went to the parking lot, came back in. So if you did that, then in those cases, you don't want to do this two-stage aggregation because that's going to be more expensive, right? So this cardinality estimation and how it plays with the costing, it is very crucial to get it right. Otherwise, your eagerag will be quite expensive. So we want to minimize. We are trying to do more extensive cardinality testing for this particular case because you could make a wrong decision, and we have already found in one or two cases that it's a tie and it could go either way. So we want to figure that out. So we want to make sure that what you get as a GA product is fully vetted for all user cases. So because of those false positives that we are getting, we are trying to make our cardinality estimation better and make it a GA as a full feature. So the feature itself is quite okay, but only the cardinality estimation needs some tweaking. Because for example, you could have skew. You can have skew between two things which could get your cardinality estimation off. So in summary for what we have covered today, so we have join optimization, which is great. You need to do that. It's bread and butter. And with 30 years of research and a lot of people looking at it, we have an amazing join ordering algorithm that Postgres have developed, which GPDB is based out of. And then you have everything else, which is correlated queries, aggregate queries. And within correlated queries, we saw two things. One is correlated queries in the disjunctive filters in subqueries, as well as correlated queries in the project list, which is the select class. And in aggregates, we found the same principle, where how to do when you have set operations and how do you do with join operations. So those are my general, a small taste out of how GPDB handles complex queries, as well as what are the upcoming feature, which is the eagerag that is coming out in GPDB6. I'm more than happy to take some questions.
For complicated queries, aren't a lot of the choice on what's optimal data dependent?
The question is for complicated queries, doesn't the characteristics of the data play a crucial role? Is okay? Yes, you're correct. And that is precisely, you could have skew, you could have correlations, you could have how it is distributed, all of those things. So for these algorithms that have, the first three especially, all of them have been vetted to see if I do that optimization, am I going to be worse off than not? It is not a heuristic. It is a rule that is applied, and you come up with a plan, and then you say, is that plan better than not doing it? So for the last one, eager-ag, again, it's the same principle where if you implement it and if you don't implement it. The only problem where it happens is the correlation between the join, because you have a join as well as aggregation, right? So you have join columns as well as aggregation columns, and the interplay between them. It's a little bit, we need to make our cardinality estimation a little bit stronger to say, hey, this may be a risky thing, or this may don't do it. So we saw one or two queries where we could, if it's a tie, we could pick a wrong plan.
And those cost estimates are pretty accurate.
Correct. Cost estimate, given that model is accurate. Okay, whether that model realistically, it's a model based out of some testings on your hardware that we have tested. So yeah. Any other questions?
Can users the algorithm choices depending on what they observe in their actual data?
That's a wonderful question. The question is, can I know that this particular optimization is useful for me or not? I know my data better than when, I know my data because it's my data. And can I tell for this query, do it, and this query, don't do it? So the knobs that are provided that the optimizer enable can be set at the query level, at the session level, and at the database level. So if that's why we would love to get feedback from everybody, is that you know your data. So we have knobs. So even when it goes fully GA and it's enabled by default, and if you found there is some skew here, which is you can't capture it by statistics or something, and I know that this is not going to work. So you can give a hint. If not all enterprise software give hints to the query. The query saying that, hey, for this query, don't do it. This query, this is a selectivity. So this would be a hint to the optimizer saying, hey, don't do this optimization. But it can be tuned for query session as well as the database. Cool. Awesome. Well, thank you so much, everybody, for joining me, both in person and at live. We'll see you with another series soon. Thanks.